Good morning, I'm Viren.
My name's Robin.
Gabriel.
I want to play a quick simulation game with y'all. Make your clothes 45 times heavier. And let's fill this room in with smoke. Uncomfortable, isn't it? We've learned two things from this simulation game. I'm really bad at making simulation games. And number two, the lives of firefighters are often in hazardous situations worse compared to this one. Imagine calling out for help, but there was no way to communicate with the outside world. That's what our project hopes to overcome. Our sponsors at the University of New Mexico have designed a system that is able to compile and transmit necessary information to headquarters. Why exactly do we need this system?
So the National Fire Protection Association currently holds a standard for Personal Alert Safety Systems, or PASS for short. These devices usually consist of a simple signal to alert others of a firefighter in distress, and on occasion, a GPS to track a firefighter's current location. We are currently working with the University of New Mexico to design a next generation PASS communication node that firefighters or any personnel in high stakes environments can wear to track vital information, including heart rate, temperature, respiration rate, and even images of a firefighter's current location. Within this system, firefighters will wear sensors on their body that transmits this information to a microcontroller that will broadcast the signal to relay nodes placed in key locations around a building. These relay nodes will take that information and rebroadcast it within a mesh network to increase the effective range of the system. These relay nodes will update the timestamp and pass them along to a base station for evaluation.
So our goal is to take the proof of concept relay system that UNM created and to optimize it. The current system consists of a RF24 radio module attached to a Raspberry Pi. With some research, we determined that this is not ideal for the kind of environment firefighters are dealing with. In this kind of situation, you want a system that's power efficient, low cost, and really simple to set up. So we researched several microcontrollers that would meet these performance needs while enabling the same kind of functionality that is possible with the Raspberry Pi. And we found that by transitioning from the Pi to a Teensy development board, we're able to reduce the power consumption by 90%, which also leads to a 43% decrease in max core temperature. So essentially, we're removing the unnecessary features that are provided in the Pi for a more streamlined system. We're also able to reduce the cost of the relay by 25%.
So we estimate to improve this whole system. Our next step is to configure this system and to begin full-fledged field testing. We thank you for your time. Any questions?
Physically, R24 relay, physically, where does that reside?
So in the whole system, or so right now we have it connected with wires.
Just jump wires.
I mean, out in the field, in a real application.
Right. So it'll be connected with wires to the Teensy, which would be the microcontroller, and that would be placed down in optimum locations to increase the range of the communication.
Okay, so these placed around a fire, so in other words, a building that's on fire, you're gonna have somebody going around the building and placing these units on all four corners of the building, or so to speak, so that it can basically triangulate where that firefighter is?
Preferably one relay for each room that a firefighter encounters.
Are they gonna remember to pick them up when they're done?
Well, that's where the price comes in.
Is there a polling rate on this? How can you have the poll actually read each firefighter?
I beg your pardon.
Is there a rate of polling on this, like how often you're seeing each sensor?
Right now we're thinking about 1 second, but we're going to boost the system, and it's all dependent on how fast we can transmit these bits across. And it's dependent on the sensitivity. So we found out that at 2 megabits per second, we have a lower sensitivity than at 250 kilobits per second.
So what kind of algorithm are you running if one of the relays all of a sudden stops working? How's the data going to reroute?
So we're actually using a third-party API to handle the mesh network. It's built on top of another layer for the mesh network, and it essentially handles all the routing and addressing. And the script itself just requires a simple ID for each node. So.
What's the relationship with University of New Mexico? You know, why aren't they building their own system?
So
Can I answer that?
Sure.
We had a conference last spring where we had 13 different universities came in. They brought in their top ECE teams, and the different instructors from the different universities said, maybe we should try some kind of experiment where instead of just, have just one university working on a problem to try to spread out. So this was kind of an experiment in intra-university senior design. It's kind of an ongoing experiment. We're just trying to learn how to do senior design better. Is that the way y'all see it?
Right.
Yeah.
So it seemed to be a key metric for this kind of system would be the range between the nodes. Obviously, you're going to measure for resilience, but that's something that you're not measuring here, and I think it would be a key care about for anyone that was looking at this product. So that needs to be folded into your objectives, and then
So
figure
the
out
forum
some
right now-
metric to use to measure that, whatever's available to you within the.
So right now, the forums say that the max range is 100 meters, and for 200 packets that are sent across, there's only be one drop. So that's something we're gonna try and
So you're gonna find 100 meters somewhere to.
Yeah, essentially.
What about in a more enclosed space? Because obviously firefighters don't usually fight fires on the football field, but
Right.
Is there any consideration for testing it in more of a realistic environment, or even just this building?
Yeah, we were talking about that, by next semester, we want to try to get a more realistic environment, maybe simulate smoke and all of it.
So for example, take this room. That door, maybe right at the corner, we put down the relay node. At that door, we put down the relay node. At that door, we put down the relay node, and we see how everything responds.
Yeah, I would be more interested if you picked different rooms, because that's the real
Right,
environment.
of course, so maybe that one.
Oh, yeah.
Outside.
What do you do if you've got a building that's got 100 stories? So with that, and let's say 10 of them are on fire. And so you're trying to put that out. I'm not going to make a reference to 9/11, but in other words, something catastrophic. How are you going to be able to, 100 meters is going to dissipate really quickly. So how is that, the range is really going to come into being something very important. So how do you get around that?
So right now, we're just thinking about a single story, so just in one particular room. But I think to better answer your question, maybe we would set up a communication between two relays that would sort of, if the base station is down here, we send the packets across and they go vertically down and over to the headquarters or to the base station for evaluation.
You can also use a drone.
How about as a fire changes, and as the previous question was about catastrophic structure changes, RF interference, you're counting on that 100 meters. How are you going to simulate or anticipate some of that interference? That will come for sure.
So we were thinking about getting a smoke chamber, some sort of a container. We put down the relay inside it, and we try to send the signal across.
You may want to think about other things like cinder blocks, building materials, girders, other things like that Bluetooth and low energy may absolutely won't go through. So, and as the building changes in size or factor, or the room changes in size and factor as it gets destroyed, that may be a key thing.